let's go ahead and look at another example. This is number 37 in the same chapter. In this example, we have a table with a box on top of it. We're going to assume the box or the table is more or less frictionless just for the sake of argument here. And we're going to shoot a bullet into this box at a very high velocity. So a very low mass object. We're going to shoot it into the box at a very high velocity. This bullet has a mass of 200 grams. And the mass of our box is equal to 1.5 kilograms. And the velocity of this projectile is 400 meters per second. And what's going to happen here is this is going to come in here, it's going to embed into the box, and then they're going to move off together at some new velocity. And the question is, how much does this box velocity change, and what is the impulse of the bullet on the crate or on the box, and what is the impulse of the box on the bullet? So our strategy for this one is going to be looking at conservation of momentum, and with all these conservation of momentum problems, I always start off, I write down the initial and the final momentum that I have for the problem, because those have to be equal to each other. So the initial momentum is going to be the mass of the bullet times the velocity of the bullet, because that's the only thing that's moving, plus 0 for the box, because the box is not moving. Now in my final momentum, I'm going to have the momentum of the bullet times some new velocity plus the momentum of the box times that same new velocity, because they're going to move off together. So effectively, we just have one object with this mass times whatever this new velocity is. And so from this, I can compute what the change in velocity is going to be. The bullet's going to come in at VB, and they're both going to go out together at V new. So I can just set those things equal to each other, so that gives me MB. VB is equal to MB plus M box times V new. And so that means my new velocity is going to be the ratio of the mass of the bullet to the total mass of both of them together times the old velocity. And this does what we expect it to do, because if I take the mass of the bullet and I divide it by the total mass, that's a number that's less than 1, and so the new velocity is going to be less than the initial velocity of the bullet, which makes sense. And we can go ahead and plug some numbers in there to see what happens, but I'm going to leave that way for a second while we answer the rest of the questions here. So the next thing it asks is, what's the impulse of the bullet on the box and the box on the bullet? Now Newton's third law, we can kind of predict what's going to happen here. Newton's third law says that the force that the bullet is exerting on the box is equal and opposite to the force of the box on the bullet. And that means that the impulse, if the forces are equal and the time they're interacting are equal, the impulses should be equal. So if we calculate the impulse of the bullet on the box, that should be the same as the box on the bullet. Now if you remember, the impulse, which is this force over time, that's equal to the change in momentum. So we're just going to look at the left-hand side of this, and we're going to ask, okay, what's the change in momentum of the bullet as it goes from VB to some smaller V new? Okay, so we're going to ignore the box for the moment, and we're just going to ask, well, what happened to the bullet when it changed its momentum? So that means the impulse here, which is going to be the change in momentum, P, the impulse is just going to be the mass of the bullet at the original velocity minus the mass of the bullet at the new velocity, right? And we have an expression for the new velocity. It's right there, so I can say that's the mass of the bullet times the velocity of the bullet minus the mass of the bullet times the mass of the bullet over the mass of the bullet plus the mass of the box times my original velocity. So I'm just going to pull out some factors here, and I should get m, b, vb, and I get 1 minus mb over mb plus m box. Okay. And let's make sure that makes sense. We start with the original momentum here. This is a number that is going to be less than 1, so we get 1 minus a number less than 1, which means the impulse is going to be whatever numerical value that is. Okay, so now let's look at the right-hand side and look at the impulse of the box. So the impulse of the box, it starts without having any velocity, so the impulse is just going to be the mass of the box times this new velocity. Oops. So I'll put in my expression for v nu. That means I get the mass of the box times the mass of the bullet divided by the sum of the mass of the box and the bullet, all times the original velocity. Now I said that these two impulses should be the same, and they don't look the same. I mean, if I look at these, algebraic expressions, they don't look the same, but it turns out that they actually are the same. Because if I take this one over here and I imagine, putting this all under a common denominator, right, I can make this look like that. So for example, I can take, let's just put this on another page. I can take MB VB 1 minus MB over MB plus M box, and I can put that under a common denominator. So I'm going to take this right here and just put it under a common denominator. So that's going to be MB VB, and this means this is going to be MB plus M box over MB plus M box minus MB over MB plus M box, right? And then if I look at that, those are going to cancel, and I'm going to wind up with MB M box over MB plus M box times VB, which is exactly what we have right here. So that is great. The momentums are the same, or sorry, I should say the change momentums are the same, and the impulses are the forces of those impulses are operating in opposite directions. So if I go ahead and compute that, if I put in 1.5 for the mass of the box, I put in 0.2 the mass of the bullet, and then I add those together at the bottom, and I multiply that whole thing by my original velocity, which was, I don't remember, 400 meters per second. So I multiplied that by the whole original velocity, 400 meters per second. And those units work out because I have mass times mass divided by mass. So I have a mass times velocity, that's change momentum. And this whole thing becomes about 70.5, if my calculator is right, in kilograms meters per second. Okay, so that's the impulse. And the impulse on the bullet is acting in that direction. The impulse on the box is acting in that direction. Now, I don't really know what that number means, so what I'm going to do is ask what's the force that is being exerted on the bullet. And in order to do that, I have to know how long it takes for this change to happen. So if I used a high-speed camera, I'd find out that this time change during this impact is something like there's about 3 milliseconds, which is 0.003 seconds. So if I take my impulse and divide it by the time, that's going to give me the force. And so if I do that, I get 70.5 kilograms meters per second divided by seconds, right? And that's going to give me 0.003 seconds. That's going to give me 23,000. And then the unit kilogram meters per second squared is just a force, so we call that newtons, which is a very large force that's acting on the bullet and the box.